Hello, everyone, and welcome. My name is Scott Phillips, and I work for Axiom Optics. Welcome to our webinar, SPAD Cameras and Arrays, an alternative to PMT, EMCCD, and ICCD. This webinar is co-sponsored by Pi Imaging, leading SPAD manufacturer, and Axiom Optics, US distributor for these products. During the course of this webinar, there's going to be a number of simple questions that are going to pop up in your chat bar on the side. We really appreciate your responses. I think the first question should already be up there. And these are just to help us understand who's here and why. So please take a moment and answer those questions. So before we get started, excuse me, I really wanted to just share a little bit about why we at Axiom are so excited about these products. So we took a laser and we put it through a water bath, and in that water bath we had a little vial of water in the first set, and then the second set we changed that vial being full of oil, and the oil of course will fluoresce, and you're going to see that in a second here. So what we showed off here is the gating capability of this camera. We're really excited about the gating capability of these SPAD cameras. We can actually visualize the laser pulse going through the water, and in this case we see it the oil lights up with fluorescence. And then we're able to capture that fluorescence signal as it lingers long after the laser pulse has disappeared. And when I say long after the laser pulse has disappeared, a whopping 10 nanoseconds. So we're going to see a repeat of that video side by side, the laser coming in, seeing the fluorescence, and then doing a simple image analysis looking at the intensity. We can see, oh, where's my laser pointer? There it is. We can see that fluorescence decay curve in the oil. So that's one aspect that we're really excited about. The second thing that SPADs are really, really good at is the sensitivity. So really single photon sensitivity. Now, I understand that the topic of this webinar was SPAD as a replacement for EMCCD, PMT, and ICCD. Well, I didn't have any of those lying around the lab, but I did have a CMOS, a very good CMOS camera. And so I did a quick little comparison. This is a very low light condition. It's 100 microsecond exposure. We're looking at an Argo light slide. So we expect the power, the sensitivity to be very consistent over time. And then in the bottom chart, what we're seeing here is an intensity profile of this yellow line that crosses this pattern. So with the SPAD, see a very clear signal of 6 or 7 photons being captured over a background of 1. And that while even your eye is great at pulling out that image, it really gets lost in the noise and the intensity. Now you might say that that's not a fair comparison because the pixels on the CMOS are so much smaller. Well, I was able to mathematically bin 3 by 3 to give the CMOS an effective pixel size of 19.5 microns, giving it an advantage over the SPAD. And even there, if I'm generous, that's a signal to noise ratio of 2, where we still have a signal to noise ratio of 6. Well, I haven't changed anything on the SPAD, so of course it's the same. So gating and sensitivity are 2 of the reasons that we're really excited about SPADs. The third is speed, and Pi Imaging later in the talk will be talking about all 3 of those and give you some examples. Before we jump into the meat of the talk, I'd like to tell you a little bit about Axiom Optics. We are a optics distribution company. We have salespeople located across the US. And the thing that I find really unique about Axiom is that the sales team is not divided into geographic regions, but rather we divide it up by expertise. So if you call and you want information about a hexapod, we're going to put you in touch with somebody who knows all about hexapods. Same for IR cameras, scientific cameras, lasers, whatever it is you're looking for. So I spent a lot of time on this slide. Might not be evident. I had it different colors and I had all sorts of animations flying in from the right and left. And it turns out that there's just no exciting way to inform people about the hundreds of different products that Axiom Optics sales and services. So I'm not going to try to list them all, and just suffice it to say, if it's optics related, please just give us a call. So as I stated earlier, there will be 4 questions that arrive in the chat bar during this talk. We would greatly appreciate your responses to these questions. If you haven't answered question 1, please do so. I think question 2 is going to be up very shortly if it's not up there already. So We really appreciate your response. Question 3 is going to pop up in just a minute. In the meantime, let me introduce our speakers. We're very excited to be co-sponsoring this webinar. We have 2 speakers from Axiom Optics that are going to really delve into the technical details of single photon avalanche diode technology. And they will be available to answer your questions at the end of the webinar. In that same chat bar where you're seeing the questions, you can put a question, and note there is a tab that is specifically for Q&A. So put questions in either of those 2 places, and we will try to get to as many as we possibly can at the end of the talk. So Michel Antolović did his postdoctoral work at EPFL in Lausanne on next generation SPADs after receiving his PhD from the Delft Technology University in the Netherlands. And despite a relatively short academic career, he was winner of both the LC Koo Award for Young Researchers and the PicoQuant Young Investigator Award. Ming-Lo Wu has a background in semiconductor and device physics. He earned his PhD from EPFL in Lausanne, where he worked in the Advanced Quantum Architecture Lab on SPAD-based systems. During his PhD, he co-authored over 10 articles, accumulating more than 500 citations. So with that, sit back, prepare to learn about this exciting new technology from these 2 experts. I will pass it over to Ming-Lo and Michel.
Okay, thank you, Scott, for the introduction. So I'm gonna share our slides. So in today's webinar, we're gonna go through it and show you how SPADs, or single photon avalanche diodes, are revolutionizing the world of imaging. We will show you how we can help generating these super resolution microscopy images. But first, let's see why and when SPAD array and SPAD image sensors are helpful. So SPADs are known to have exceptionally high readability or fidelity for low light signals. So this is quantified by having a high signals to noise ratio in low light condition. And also SPAD have extreme precise timing. This is quantified by a low standard deviation or a very good timing precision down to picosecond. So when we talk about low light condition, we're talking about few hundreds of photons down to even single photon. So in these applications, such as photon counting, that is used in quantum application or single particle imaging, you can see that the signals to noise ratio of SPAD is better than a conventional photodiode and in a very low impinging photon count. On the right, you can see a comparison of SPAD and a photodiode under just 10 impinging photons. You can see that the SPAD image has a better signals to noise ratio. So in conjunction with low light application, there's also high speed application, such as confocal microscopy, where you need to scan over space and time. So when it is high speed, naturally, you are also exposing to the sample much shorter, which means you will get less light. And this goes back to the low light condition. And the third scenario is for timing applications, such as fluorescence lifetime imaging and other type of time resolve imaging applications. So a quick introduction to SPADs. So how do a normal optical sensor work is that it converts photon into charges. And by accumulating these charges, this gives you a different intensity in the electrical signals. And once you have each pixel having different intensity, this gives you an image. So what's different, how SPAD is working differently is that it's working in Geiger mode. So in Geiger mode, this amplification of the charges has an infinite gain. So this leads to a direct photon to digital transformation. In other words, SPAD works as a photon transducer to a digital signal. So a single photon can create an avalanche current that's with the infinite gain. This gives you a high level of 1. And when there's no photon, there's no current, it gives you a low level 0. So it gives you this digital response with ones and zeros. So this gives us the capability to do photon counting. And since this is a digital response, there's no readout or excess noise to be considered. And as mentioned, this avalanche process is extremely fast, down to picosecond timescale. So we will also get the timing precision of the timing of these photons. So what does a 1-bit information look like? So now we're pointing our camera to a target that's shown on the left. So on the right side, you will see a 1-bit image. So this image is only consists of ones and zeros. But if we accumulate this longer to build up the statistic to a multi-bit image, this image becomes more of an image that we are used to. And you see the signals to noise ratio improve dramatically. So how is this better than normal camera? It's give you more information down to single photon resolution in a 1-bit mode. So the SPAD also has timing capability. As I mentioned, this can be done by adding a timing circuit over the readout circuit itself. So the timing of the photon arrival can be time tagged directly. And as mentioned, this is done in the picosecond timing scale. We can also use time gating. So in time gating, we define a very short exposure gate with respect to the reference signal. This reference signal is usually a pulse light source, such as a pulse laser. So if we see a photon within the gate, we know that the exact timing of the arrival of these photons. So with this, we get the time of flight information and also the timing information of illuminating object, for example, like in fluorescence samples. So in this example, we're using the gating capability to observe light in flight. So with the resolution down to 20 picosecond, we can observe the laser front traveling in this media. And with further processing, we can even see how the laser light scatters within this box filled with this medium. So now I'm going to give the floor to Michel. He's going to tell you the comparison between SPAD and the existing technologies.
Thank you, Milo. Thank you very much. Thank you very much for the great introduction. We will dwell now into the details of how SPADs compare to other technologies. Before we do that, I would like to emphasize the fact that we have 3 types of SPAD arrays: point, line, and image sensors. When I say point, I still mean a small SPAD array, just limited in the number of pixels. Line is intuitive, and an image sensor is something which represents more a camera. I'll start with the point detectors, specifically point detectors used for confocal microscopy, where we have 3 main competitors: PMTs, hybrid detectors, and custom-made single pixel SPADs, or APDs. The main purpose of SPAD arrays is to overcome all of these other detectors and to be better than them in all aspects. We specifically focused on solving the challenges that we have in these other detectors. For example, PMT is known to be a very good detector with high dynamic range and large active area. However, it suffers in low signal-to-noise ratio due to the following facts: multiplication noise, after pulsing, and limited sensitivity. Hybrid detectors, they offer as well high dynamic range, but they have no integration capability with other functionality and no pixelation. The same goes for custom-made single pixels, or APDs. They have no pixelation, and in addition to that, limited dynamic range. SPAD arrays offer you to have really high sensitivity, not only high peak sensitivity, but also, in contrast to PMTs and hybrid detectors, a very wide spectral detection conditions. And then in conjunction with the large number of pixels, we offer high dynamic range and great timing resolution. Not to mention that, of course, PMTs are bulky compared to SPAD arrays, which are sized in the millimeter range. If we dwell into the SNR comparison, I would like to start with comparing analog PMTs with SPAD arrays. On this slide, I'm showing you the comparison of an analog gas PMT, where the illumination was 520 nanometers, with an average impinging signal of 10 photons. On the following slide, I'm showing you the comparison at 50 photons, and now I'm switching to a counting gas. The main difference between an analog gas PMT and counting gas PMT is that we are taking away the excess noise, but we are, because of that, reducing tremendously the dynamic range, and we're also introducing afterpulsing. So the situation improves a bit, but SPADs are still winning in this case due to their increased sensitivity. Again, you can see a similar comparison at 50 impinging photons, and then we are switching to 700 nanometers illumination, which is really the edge where PMTs still make sense, especially specifically in this case, the gas PMTs. Their sensitivity drops significantly after 700 nanometers and diminishes to 0 almost afterwards. In contrast to SPADs, which have extremely good sensitivity all the way to 950 nanometers. So the increased signal-to-noise ratio comes in conjunction with a really high dynamic range. On this slide, we are focusing on the response of the SPAD on the left-hand side and the signal-to-noise ratio at the same light conditions. And you can see what the pixelation or the pixel parallelization does to the dynamic range. For example, our detector here, SPAD lambda, which is the linear detector, can, in a single pixel arrangement, operate all the way to 130 megacounts per second illumination. And then if you apply pixel grouping, it goes all the way up to 1 gigacount per second, as I indicate here with the yellow line. Okay, for the point detector SPAD 23, the situation is slightly different, but the same principle applies. So if you look at 1 pixel, the count rate that one can observe is 7.6 megacounts per second, which expands to 172 megacounts per second for the whole detector itself, offering really an increase in the dynamic range. So now I will switch more to comparisons between cameras and image sensors. And I would like to reiterate the fact that we are really a digital camera. When I say we, then I mean SPADs. So deep is my connection with SPADs. Compared to other analog sensors like CMOS, scientific CMOS, EMCCD, and as well ICCDs. When we look at the details of an EMCCD implementation, they offer high sensitivity and low effective readout noise, mostly because of their electron multiplication, which however comes at the cost of excess noise, which effectively reduces the signal-to-noise ratio by a factor of square root of 2. And due to their architecture that you can see here on the left-hand side, and everything being serialized, they are really limited in speed. Scientific CMOS image sensors, they offer certain parallelization of the readouts, mostly by introducing the column amplifiers and analog to digital converters, as you can see here on the image as well. This allows them to increase the speed, and due to the fact that they do not have electron multiplication, they do not have excess noise. However, the disadvantage is they still have readout noise, and they have mismatch in column amplifiers, which increases the non-uniformity and has an effect as well in the final signal-to-noise ratio evaluation. SPAD imagers, they bring this parallelization one step further by introducing the digitalization directly on the pixel. So we go from whole image sensor serializer in EMCCDs to columns, readouts in scientific CMOS, and then to pixel readout in SPADs, offering really the possibility to read out extremely fast at no readout noise. Of course, not to specifically mention, SPADs do not have any excess noise. How is this possibility to count photons translated in some data? Here we are showing you an input on the left-hand side, 1 photon, 2 photons, 3 photons, 4 photons. When we switch to light detection, for example, with SPAD image sensor, we of course introduce Poisson statistics or Poisson distribution. This is the best that you can get and limited by the quantum nature of light. And you can still see discrete levels, which are really easily distinguishable. So if the average photon flux is 1, we'll sometimes get 0, sometimes 1, sometimes 2, sometimes 3, sometimes 4. How does this change if you represent it in a histogram? So you can see here the distribution of output photons based on an average flux of 1. And you can see that the levels of photons is really easily distinguishable. It's discrete quantized. If you represent the same output for an EMCCD, you can already see here on the right-hand side that the levels become very blurry. It's not it's not easily distinguishable what's 0, what's 1, what's 2, and so on. And this is due to the excess noise and also due to the readout noise. You can see what is the difference between the distribution of photons and the output between a SPAD on the left-hand side and an EMCCD. What is here a 0, what is a 1? It's really difficult to say. Where do I put the threshold? Of course, I put the threshold at the minimum probability, here indicated by my mouse, but I'll still have false 1s, false 0s, and false 2s. The situation improves a bit for scientific CMOS because, of course, we eliminate the excess noise. However, because of the readouts, the distribution is still blurry, and we have not really a clear Poisson distribution, but more something that we call a hand diagram. So you can see, the individual distribution or probabilities for photon levels being a bit higher and then representing fingers. And you can appreciate that now, of course, this distribution looks more like the SPAD distribution, but it's far from ideal. Now, summarizing, what does a SPAD give us? It gives us the best photon counting fidelity at extremely high frame rates. This is really the key takeaway. Low light, extremely high frame rates. Of course, we also fairly state that we still have work to increase the pixel resolution. Our current image sensor is 5 tall square compared to maybe some other implementations in scientific CMOS, which have slightly higher pixel resolution. Okay, to quantify a bit the low light capabilities, we also make SNR comparisons between a scientific CMOS and a SPAD. You can see the results at 0.6 lux and at 0.1 lux. And you can see the signal to noise ratio plot as well. So what do we see here on the right-hand side? You can see the black line, which is ideal Poissonian distribution. Then we are dropping from this ideal distribution because we have sensitivity. So we are detecting every second photon, but it's still Poissonian perfect line. You see then when we increase the integration time of a SPAD to 5 milliseconds, we have a small influence of the dark count rate here in this left part of the curve. This is of course there because we accumulate just more dark counts. And this is also important in conjunction with the fact that we do want to operate the SPAD at the highest frame rate or short integration time. However, even with relatively long exposure times, you can see that the signal-to-noise ratio of scientific CMOS camera is significantly lower at less than 100 photons impinging. Okay, then further to high-speed capability, I would like to show you a fan going imaged at normal speed and then all the way increasing to 100,000 frames per second. You can see that the SPAD image sensors are operated in global shutter mode, where the frame rate can be disentangled from the exposure. Here we see at the end 1 bit video with 100,000 frames per second. And then we have different examples with different frame rates offering the capability to capture really fast motions. Okay, how does this translate to the products that we are offering? We have, as mentioned before, 3 product lines: point line and image sensor. Our technology comes with a peak photon detection probability above 50%. All of our products have microlenses in the offering. The typical dark current rate is below 100 counts per second, and even smaller for our image sensors. If you tableize the products, we have a point detector, SPAD 23, a line sensor, SPAD lambda, and an image sensor 5² They differ a bit in what they offer as operating mode. All of them have photon counting, so just frame-based readouts where you get the photon counts. And then the point and line sensors, they have time tagging, as explained before. And then the line and image sensors have time gating. When you go from small arrays to big arrays, you can also see that the maximum throughput of the photons increases tremendously. What's important is, again, to emphasize the extremely high frame rates, as you can see here in the one to the last row, and then the timing precision, which is in picosecond range. Okay. To reiterate the measurements conditions that we want to target with SPADs, whether this is photon counting, time gating, or time tagging, we typically want to be below 300 photons per integration. We want to have the integration time typically less than 10 milliseconds. And we offer in these various operating schemes different timing resolutions. So if you do photon counting, the timing resolution is limited by the frame readout. So typically 1 microsecond resolution. If you're doing time gating or time tagging, the resolution is defined either by the rising edges of the gate or by the time tagging instrumentation response function, which is in the range of 100 picoseconds. Okay, we'll focus now on the applications. I will start with quantum applications, which are, of course, detailing anti-bunching, coincidence correlation, and as well quantum random number generation. Here I show an example of continuous heralding control of voxel beams using our SPAD image sensor. You can see really nice coincidences. And as well here, this was one of the first full quantum imaging experiments done with high-resolution SPAD image sensors. To really quantify, again, why SPADs are ideal, because of the fidelity of photon counting, as mentioned before. But it's not only that, it's also about the acquisition speed. And here we have an example of different detectors and how long it would take them to read out 1,000 and 10,000 frames at a given 5² resolution. So you can see in the 1-bit mode, we have a factor of 100 minimally. And if you go to 4-bit mode, then this trims down slightly, but the difference in the acquisition speed is just tremendous. Now imagine if you're doing either an application development, system integration, or anything similar, how much this will help you. Now we are switching to confocal microscopy in conjunction with the signal-to-noise ratio and, of course, the dynamic range. SPAD arrays offer you to have super resolution imaging. Here I would like to emphasize the great work of our friends from Picoquant as well, showing the difference between just normal confocal imaging and then confocal imaging enabled by SPAD arrays, improving the resolution by a factor of approximately 2. You can see more details than on this slide, where we go from a blurry image like here on the left-hand side, and then being able to differentiate 2 different fluorophores within the sample because of the time tagging that we have, and then mapping that all together in a beautiful color image with super high resolution. If you want to quantify, as I mentioned, the resolution improvement, this is typically a factor of all the way to 2. So we go from approximately 200 nanometers diffraction limited resolution to all the way 100, 120 nanometers resolution. Okay, so I would like to then focus on the final application, which is FLIM, fluorescence lifetime imaging, specifically focusing on how we can overcome some FLIM instrumentation drawbacks. Of course, if you're an expert in FLIM, you're familiar with pileup. A pileup is an effect that causes you to wrongly estimate the lifetime of your sample if you have too much light. And the recommended detection rate is, okay, you can have a detection rate which is 1 to 10% of your laser repetition rate. So if I use the specific parameters as given here on the right-hand side, we can see that the FLIM frame rate is approximately 0.08 frames per second. In conjunction with the pileup, then of course the best FLIM instruments have a requirement to have X and Y scanners, which is quite complex as well. So for that, we are offering, of course, 2 solutions. We are offering SPAD arrays, which overcome the pileup constraint. And we also offer image sensors for FLIM, which overcome both the pileup and the requirement to have scanners. So if you have if you do 2 calculations, one calculation is based on illuminating with point spread function, area disk illumination. We increase the frame rate of the FLIM by a factor of 5. If you do spread the light uniformly, we can increase the frame rate by 23. And then the big change really in frame rate comes when you use the image sensor, which really enables us to have tremendous data throughput due to pixel parallelization. Okay. Here I highlight great work of our friend who is also, I believe in this webinar, Xavier Michelet, who did a comparison with EMCCD and the SPAD image sensor, the predecessor of 5-square. More details can be found on this publication. And I would like to finalize the presentation just by showing the different data throughputs that we have in SPAD image sensors and what frame rate this enables, going all the way to really video rate FLIM. Okay, with that, I would like to thank you, and I'd be glad to take some questions. And of course, Scott will come back to the pools as well.
Great, thank you so much. It was a great presentation, and we did get a number of questions. So let's just jump right into questions. Well, before I do that, I will mention that there are still some questions in the sidebar that we're looking for your responses from. But in answer to your questions, the first question was, this is single photon sensitive, not single photon counting. Is that correct? So you can't know if 3 photons arrived in a unit of time.
So if you talk about 1 pixel, this is correct. Here we are talking about SPAD arrays, so this is incorrect. So if you distribute light over multiple pixels, then we can differentiate between 0 all the way to the number of pixels representing the maximum number of photons that we can capture at the same time.
So I'm just going to add to that it is true that you only capture a single photon in a single time point, right? It's either it is, as you stated, digital. You find a photon, it's not, and within that very, very short exposure time down to 6 nanoseconds, you're only going to detect 1 photon.
For 1 pixel, correct, yes.
There was a question about resolution. So the pictures appeared to be very high resolution, even for PMTs. Do the pixel images correspond to the number of pixels in the SPAD array? So certainly for the images I showed, I did no doctoring of those images.
That's correct. So for the image sensors, of course, there is no scanning, so the resolution is 5 square. And then for the point detectors, we of course applied scanning. So the resolution of point detectors is not limited by the pixel number, but it's limited by how fast you can scan.
There was a point of clarification when you were comparing the SPAD and the CMOS. Can you go back and elaborate on why the dart count rate increased with the longer integration time?
Mm-hmm. Absolutely. Okay, yes. So just to clarify, the dart count rate did not change. It's only the dart counts which are accumulated that have been increased. So let's say if you have a dart count rate in our image sensor of approximately 5 counts per second, or let's say it's 10, then we need to multiply this dart count rate with either 0.1 milliseconds, in this case, 1 millisecond or 5 milliseconds. So it's just that the dart counts accumulated during a longer period will be higher.
Yeah, great, thank you. So question about LiDAR. What are the potential challenges in cost reduction for mass market applications such as LiDAR? So just that's something you see in the future.
So LiDAR has been one of the fields that SPADs attacked really early on. Mass adaptation or cost reduction requires to focus on a single application, fixate not only the image sensor or detector, but also the system, and then mass produce it in high volume. Of course, high volume reduces the price. So in principle, the cost structure for high volume for SPADs is very similar to scientific CMOS or CMOS in general.
Great, thank you. What is the size of individual SPAD when imaging in 512 by 512? So I believe the question is, what's the pixel size?
The pixel pitch is 16 micrometers. And then we have 2 options. Either we can have microonces, which then of course the sensitive area is 16 micrometers. Without the microonces is 6.5.
And what about the other 2 detectors that you offer?
The other 2 are 23.5 and 29 micrometers.
Thank you. So a question about ICCDs. How do SPADs compare in terms of quantum efficiency with ICCDs, where you can tune the process to get very high values from UV through the IR?
EMCCDs have quantum efficiency north of 80%. However, because of the excess noise, this quantum efficiency is effectively halved if you look at the signal-to-noise ratio. So we are actually looking at effective sensitivity between 40 and 45, which is then the exact same level that we have for SPADs. We have photon detection probability in the range of 40 to 45%, including the microlenses.
The question was specifically about ICCDs and tuning the sensor to move that QE from UV to IR.
Mm-hmm. So ICCDs operate with a photocathode, and they enable you to just swap, let's say, the photocathode to change the detection range. So they do offer IV, visible, and then also near infrared. The same can holds for SPADs. One can build SPADs for UV, for visible, and red. In our company, we are focusing on visible.
And what is the effect of the temperature on QE and the sensitivity of that QE?
There is no effect.
Okay, that's an easy one. With super resolution imaging, what can you do with SPADs? So why would I want to use a SPAD for super res?
So in this webinar, we focused on confocal microscopy. Their SPADs excel because they have pixelation. So they offer you to improve the resolution by a factor of 2 purely because they have pixelation. Details on that can be found if one searches for image scanning microscopy. This is really great theoretical work done by many researchers. SPAD enable this super resolution. When we talk about other super resolution techniques, more wide field, like localization microscopy or structured elimination microscopy, or potentially SPAD. In wide field, we bring the possibility to really have high frame rates. For localization microscopy, this reduces the total acquisition time and improves the super resolution frame rate.
Great, thank you. There's a question about why SPAD image sensors are so expensive.
That I made a joke about this. It's because you need to buy more of those to have a higher volume.
Yeah, and quite honestly, I would say that they're not more expensive than the competing technologies that are available to do this level of sensitivity and or gating or speed of acquisition. So price of SPADs have come way, way down. A question about the future. What do you guys see is coming? Are we going to see multi-megapixel cameras coming soon?
For that, please subscribe to our newsletter. We would like to stay in touch with you, and of course, we will would like you to be the first one to know about anything that's coming up.
Excellent. Can you expand a little bit on what the limiting frame rate was when you showed your film data? You gave a frame rate of 30.
Yes. Finally, the frame rate is defined by the lifetime precision that you want to have. So if we are slower, we are going to accumulate more photons, and then our precision will be higher. This is the main limitation.
Okay. And can you give the fill factor as a percentage of microlens versus non-microlensed?
I do not know the percentage, but as mentioned, you can consider that the size of the microlens detector is 16 and the non-microlens is 6.5.
Okay, thank you. What is the practical dead time of a SPAD pixel?
This is in the range between 10 and 50 nanoseconds.
Great. And what is the time width of the impulse in tagging mode, and does it vary with count rate?
This is 100 picoseconds, and it does not vary with count rate. It does not vary.
And in tagging mode, what would you give as a recovery time?
The recovery time is limited by the SPAD dead time, so this will be in the range between 10 and 50 nanoseconds, depending on the detector. So for the SPAD lambda is more 10, and for SPAD 23 is more 50 nanoseconds.
Okay. Well, I think that is all the questions. Again, I would ask everybody, if they haven't answered the poll, to please do that. If you have any more questions, dump them into the Q&A. We'll stay online another couple of minutes to see if anybody has any more questions. But thank our speakers. Really appreciate your time today and the excellent presentation. I know it was informative, and I will let everybody know that this presentation has been recorded and will be available on both of our company websites in the near future.
Excellent. Thank you very much, Scott, and thank you to all the attendees. We look forward to the future of the SPADs.
Yeah, thank you.
We do too. Thank you, everyone.